All right, so let's work an example problem that will give practice working with the stoichiometric table and also changes in volumetric flow rate. So consider this example. We have a gas phase reaction, A plus 2B goes to C. It's carried out isothermally and isobarically in a fluidized CSTR with no pressure drop. The feed is stoichiometric in A and B and no C is fed. The pressure, temperature, and volumetric flow rate of the feed gas are 6 atmospheres, 170 degrees Celsius, and 50 liters per minute respectively. The rate constant is equal to 53 moles per kilogram catalyst per minute per atmosphere cubed at 300 K, and the activation energy is 80 kilojoules per mole. So for this reaction, we're going to complete the stoichiometric table, and we're going to write the rate as a function of conversion. So first, to start out, let's just draw the system. So this is a fluidized CSTR. A fluidized CSTR looks just like a normal CSTR, and this is supposed to be a square. The difference is that it's got catalyst pellets in it, so it's a catalytic reaction. So from a solution procedure, the only difference between a fluidized CSTR and a normal CSTR is that the fluidized CSTR will solve for a catalyst weight, whereas the normal CSTR will solve for a volume. So there's really, other than that, everything else we're going to do is the same. So this is different. The analog in the tubular reactor is the PFR versus the PBR. We'll get into that in a few lectures. In that case, there's a pressure drop that we have to take account by using the Ergun equation. That's not the case in the fluidized CSTR. In the fluidized CSTR, it's really just a matter of solving for a volume versus a catalyst weight. So this is my fluidized CSTR, has catalyst inside it. I have A and B coming into the reactor, and I have A, B, and C leaving the reactor. And inside the reactor, I have A plus 2B goes to C. So the first thing I want to do is create a stoichiometric table. So a stoichiometric table is basically a way to account for the different the flow rates of the different species. So the way I'm going to write that, I'm going to have a column for species. I'm going to have a column for the initial amount of each species, the change, and then the remaining, or we'll say the exiting. So the species I have here are A, B, and C. The initial amounts for A, I have FA naught, so the amount coming in. Coming in for B, I also have FB naught. But I know that the feed is stoichiometric in A and B, and that means since the stoichiometric coefficient of B is twice that of A, that means that the amount coming in of B is equal to 2 times the amount coming in of A. So I'm going to write FB naught is equal to 2 times FA naught. This allows me to decrease the number of variables I have to worry, the number of parameters I need to worry about by 1. And then if I look at C, the amount I have coming in is 0. So before we proceed, I'm not given information for what FA naught is, so let's solve for it. This is a gas phase reaction, and I'm given information about pressure, temperature, and volumetric flow rate. That means I can use the ideal gas law. So I'm going to say the flow rate of A is going to be equal to the initial mole fraction of A times the total pressure coming in times the total volumetric flow rate coming in divided by the gas constant times the initial temperature. So I could go solve that. So let's do that. So we'll say if I want to solve for FA naught, I can enter in these values. First, let's get the initial mole fraction of A, why A naught. So the mole fraction of A initially, this is a concept that you learned in chemistry. What is the initial flow rate, or I'm sorry, what is the initial mole fraction of A? So we've said that the feed to this reactor is stoichiometric in A and B, and we've said that the reaction stoichiometry is 2 moles of B for every 1 mole of A. That means that the initial mole fraction of A should be 1/3. So I get that by saying 1 mole of A divided by 1 mole of A plus 2 moles of B is equal to 1/3. So if I insert that into my equation, and I could solve, so this is the expression that I get for FA naught, and I could solve for this and get a value. And then I would have all of the values in this column. So now the change that's going on in the reactor. So this is due to the conversion, so the amount reacted. So for species A, the amount that's going to react, this is going to be a negative value. So the change is going to be negative because species A is reacting away, so it's going to be negative. And the change is going to be equal to FA naught times XA. So that's by how much is changing, or by how much the flow rate of A is changing. So that leaves me with the amount exiting the reactor as FA, which is equal to FA naught 1 minus XA, which we expect based on the development that we have come to this far in the class. So similarly for B, the change in B is going to be equal, B is a reactant, so it's going to be negative. And the change is going to be equal to the initial flow rate of B times the conversion of B. A and B are always going to be related through stoichiometry in the reaction, and since they're fed at a stoichiometric amount, we can say that the flow rate of B is always going to be equal to 2 times the flow rate of A. That means the change in the amount of B is always going to be equal to 2 times the change in the amount of A. So that means that we can say that this is equal to negative 2 FA naught XA. And similarly, my amount exiting FB is going to be equal to 2 times FA equals 2 FA naught 1 minus XA. Now for component C. Component C and component A, they have a 1-to-1 stoichiometric ratio. That means, except for that C is a product while A is a reactant, that means that the amount of C that's being formed is going to be equal to the negative of the amount of A. So that is going to be equal to FA naught times XA. And since there's no C fed, so that's my stoichiometric table. So now I want to write the rate of the reaction in terms of conversion. So I need a rate law. So let's assume elementary reaction. So I'm not given any information about what the rate law is. Because of that, I'm going to assume that it's an elementary reaction. And so to do that, I would say minus RA is equal to Ka Ca Cb squared. So I am given a rate constant. So I'm given a value with the units for this rate constant. So let's check the assumption about the elementary reaction and see that it follows what the units are for that rate constant. So if I look at my rate constant, the units are in moles per kilogram catalyst per minute for pressure cubed. So what I want for this fluidized CSTR, my rate is going to be written, I need my overall units in rate. The units on rate to moles per time per mass catalyst. And the reason for that is because the mole balance for a fluidized CSTR is written in terms of catalyst mass instead of volume. Instead of So normally a CSTR, you would be solving for the volume. In a fluidized CSTR, you're solving for the mass of catalyst, which we denote with the letter W. Because of that, we need the rate in a CSTR should be in moles per time per mass catalyst. So you see that this rate constant, the units on this set us up well for that. We've already got the mole per mass catalyst per time, but now we have this pressure term, pressure cubed term, where we had written in terms of concentration cubed. That tells me that this rate expression is going to be written in terms of pressure instead of concentration. So instead of K times Ca times Cb squared, it's going to be equal to K times Pa times Pb squared. So rate is negative Ra equals Ka times Pa times Pb squared. And recall that for gases, pressure and concentration are related. So concentration of species I is equal to the pressure of species I, or this is the partial pressure. So Yi times P tot, where Y is the mole fraction. So this rate expression will give me, this rate expression has units that work out to give the rate the correct units, and it also works with the units of the rate constant. So this is what I'm going to assume for my rate law. Okay, so now let's take this expression and write it in terms of conversion. So there's a couple of equations in the book that we can use to do this. We can use either equation 4-25 or equation 4-27. These two equations are related. This one basically allows us to write the concentration This one allows us to write the pressure, and the relationship between the two is this relationship here, that the pressure of A is a function of XA is equal to R times T times the concentration of A is a function of XA. So that's basically the relationships between these two equations. This equation is actually in terms of pressure, so I'm going to use equation 4-27. The pressure of species I is equal to PA naught times theta I plus nu I, nu is the stoichiometric coefficient, times XA. So A here is the limiting reactant, or the basis of calculation, divided by 1 plus epsilon XA times lowercase p. This lowercase p comes into play when we have pressure drop. That would be if the reactor were not isobaric. So if there was a pressure difference across the reactor, we'll see that when we work with PBRs. For fluidized CSTRs, we don't have to worry about it, at least not in this class. So P here is equal to 1. Since the reactor is isobaric. So this becomes my equation for the pressure of A and B that I can get to insert into this rate law. To solve this, I need to know this epsilon value. So epsilon is equal to YA naught times delta. Delta is an expression that gives the change in the number of moles in the reaction per mole of limiting reactant. So delta, the general formula for delta is equal to stoichiometric coefficients of the products divided by the stoichiometric coefficient of the limiting reactant minus the stoichiometric coefficients of the reactants divided by the stoichiometric coefficient of the limiting reactant. In this case, the reaction is A plus 2B goes to C. So there is no D to speak of. The stoichiometric coefficients on A and C are the same. Stoichiometric coefficient on B is 2, and the stoichiometric coefficient on A is 1. So if I take this equation, I'm going to get that delta is equal to -2. Henceforth, epsilon is going to be equal to -2/3, since I've already solved for the initial mole fraction of A. Therefore, I can write my different pressures. PA is equal to PA naught times 1 minus XA divided by 1 minus 2XA divided by 3. And I know that PB is equal to 2 times PA, because of the stoichiometric relationship between them and the fact that they were fed in stoichiometric proportions. So now I could take this information and substitute it into my expression for the rate law, and I would have the rate law written solely as a function of conversion. The only thing I would need here is this term for PA naught YA naught times P naught, or we're given that information.